There is a small interactive component to this if you want to get your laptops out and follow along. This source code is on GitHub under Hugh Sando, user Haxe Summit 2017. If you clone the repo, there's a little exercise we can do later if you're interested. Also, there's quite a lot of stuff I can go through. Whether or not I should is another question. I'll kind of leave up to you. So if you guys have any particular interests, yell out. I don't really want it to be maybe a bit more interactive and get an idea of what people are interested in without, if no one makes a comment, I'll just plow on through. But if someone's got any other ideas, I'm happy to entertain them. Yeah, but whatever you do, pay attention because there will be a test at the end. So just make sure you're listening. All right, so we're talking about linking external code and generating hxcpp externs. There's a couple of components to this. One is actually physically getting the code in there next to your Hexcode compiled and all linking in the same environment. And then there's the other component is the interacting with the code as far as memory references is a big thing to consider. Talk a little bit about the thread structure and some of the design of how the thread stuff works, and if you get a good mental picture of that, it should be easier to work out kind of what you need to do to get stuff right. And there's a few advanced topics. I can talk about custom tool chains or some other aspects if anyone's particularly interested. So looking at the mechanics of getting the code to stick together, this code's going to come in many forms. Like it could come as a source code, like a standard open source library. People can just download the source. A static library, you might be given a static library from a third party where it's got proprietary code inside and it's just got a simple API, or a framework. Even the operating system ships either static libraries or at least static libraries that kind of call it dynamic library. They still look like a static library. And then the other one is similarly dynamic libraries, which may be installed on the system. So when you write your code, you assume that the user has gone and downloaded and installed this particular SDK before you start, or maybe you provide them with the DLL in the form of NDLLs. And the goal is to expose these functions here to the Haxe user. I'm going to use the word user in this talk mainly to talk about a developer. From the perspective of a library generator, your user is another Haxe developer who wants to link in with your code, or yourself if you want to link in with your own code, if it's just a purely internal thing. So Haxlib is actually a pretty good tool for providing code with, maybe in conjunction with a third-party download instruction. So you'd have a README that says, go download the Android SDK or whatever, and then you can start using this library. And Haxlib is good if you use it in a simple way, mainly to get a directory path out of something, and also you can provide additional dependencies. So maybe in the enemy example, there's this enemy toolkit which contains like SDL and free type and ping and JPEG and all this code, which is not really the core of enemy. So I've just bundled it all into a Haxlib, so you can just go Haxlib install enemy toolkit. It's done. The enemy code now knows where to find all the paths, all the JPEG stuff, and it really is quite a convenient way to distribute source code as well as dependencies. Now, if you're providing some code to another Haxe developer, you can provide it in the form of a static library, and this is where I came from initially. With hxcpp, I would have I've had a static library for things like regex, and for NME, I would have a static library. The problem is that there are now so many different architectures you would need to provide in order to cover most scenarios that it really does become impractical. And static libraries can also get really big, especially once they get symbols in them. They can start getting huge. Like I looked at doing the WX, distributing that as a library because it takes so long to compile, but the library itself becomes enormous. So it's really not a great way of doing things. So I would suggest, unless it's trying to hide proprietary code, better to come up with an alternate solution. So in order to mitigate this issue of compile times, which is one reason not that I wouldn't provide stuff as a static library, hxcpp now has a compile cache. I'll quickly go over that. This is from the hxcpp docs directory now. It should be shipping with hxcpp. So the compile cache is a store where it stores all the object files that you create for a project. Normally, well, in the old way of doing it, object files would be created in a local directory called obj something something something, and you would just link all those together. But now I store them off in a separate location and maintain a list of them according to the most recently used one stays fresh, and the older ones I get rid of if I start running out of room. You can set the cache size here. The cache megabytes I've set here to 4,000, so that's 4 gigs of data set aside for the cache. It defaults to 1 gig, but actually that can not be enough if you do a lot of debug compiling. You can actually start thrashing the cache with a gigabyte of obj files if you're doing multiple targets with multiple debugs. And it's also nice if you set aside this on an SSD so that it's fast area, so you're just going to speed your life up significantly. Another use of the cache is to deal with some path length issues. Sometimes when you go to link up a whole big load of obj files, you can overflow the system's path length. So it can actually help to make a short path directory for your cache, like C/A. I have another little mitigating thing we can do. I'll show you, but yeah, that's another consideration. And the cache works on dependencies. So it takes your source file and looks at all its labeled dependencies, makes a big hash of them, sticks the compiler name in, adds that to the hash. So then it's got this one ID for your object file, and if any of those things change, the object file will need to be recompiled. But if all the things stay the same, you can reuse objects. And it turns out it's actually reasonably probable that you would reuse your objects between projects. Because if you've got a one source file, generates in one directory and it's exactly the same as another file in a different directory, because the hashes will be the same, it will use the same object file, and you won't need to recompile it. So this is particularly useful for these external libraries where there's not a lot of dependencies. Like you might download SDL, say version 2.1, and you can use that in multiple projects. It doesn't need to be compiled differently for each of the projects. And in that way, it kind of acts like a static library without needing to provide it to all the users. So in the cache, in order to use a project in the cache, you have to just assure hxcpp that you do not understand that you've listed the dependencies for the files, because otherwise you could change a file, like change a header file, and the cache doesn't know to update, and you get an old CPP file and you go, why isn't this recompiled? So you just need to add this cache line to your build XML file, saying yes, do cache it. And the project here as well is interesting. You can give a particular set of files a project name, and then they will be grouped together in the cache, which means you can delete them from the cache as a group, or see how much memory you're using for the files, for all those files in a particular project. And finally, the as library parameter takes all the object files in the file list and builds them into a .lib file, and then puts the .lib file on the link line to the final exe. This has a couple of consequences. One is that it shortens the path length, and it can actually get around some compilers that can't handle a huge number of object files on a command line. But another one is that when you link against the library, it only selects the object files that actually resolve a symbol. And this can have a couple of consequences. One is that you can end up with a smaller executable at the end of it because you've got these object files that do nothing, they're just actually not included. There is one downside, is that if you require an object file to be in there and it's kind of self-registering, and so there is no external link into it, but it does actually do something important and it's like a constructor, you will miss out on that file. So that's just a little trick to think about there. So if you want to have a look at some of the hxcpp cache, you can run haxe run hxcpp cache, and then one of these commands, clear list is probably a good place to start, and that'll show you the projects that you've got currently you're using, and then you can just delete the cache for a particular project and start again. So that's sort of worth a look at that. So shipping dynamic libraries actually is sort of slightly better than shipping static libraries because they're kind of immune to some of the versioning issues that happens with static libraries, like when Microsoft upgraded their compilers, their STL implementation wouldn't statically link from a new binary against an old binary, but now if you shipped as a DLL, it kind of encapsulates all those linking requirements and provides a smaller interface, and you could actually run a DLL generated with an older version of MF's Visual Studio with some newer source code. And it also, one thing it does is also bundles all the dependencies, so you don't have to say, oh, don't go download enemy toolkit if you want to compile this, because it's already sitting there compiled. You still might have to cover architectures, Win32, 64 Mac, Android. Can't do iOS because they don't accept dynamic libraries. This is actually the approach I've taken with NME. So I ship Windows, Linux and Mac DLLs. So if you want to just use those ones, you can run NME without having to do any of the compiling of the dependencies. But if you want to sort of go off-piste a little bit, you'll have to download the dependencies and statically link it all up for yourself the first time. But this isn't too bad. I'll get to build.xml files, how actually it's pretty trivial to have the one build file allow you to do either of these use cases without really having to change too much. And sometimes you might want to still leave the option of a static link, so it's going to be easier if they do a dynamic link, but maybe if the person compiles all the files themselves, they can get the latest changes without having to do a two-step thing. And it's a single exe solution, which some people like, where you just got one thing, you click it, it runs. You don't have to worry about shipping a library or anything with it. So sort of nice, even if you are going to ship a dynamic library, to also provide a way of doing the link for the user themselves. A kind of reverse way here is an executable. So you would actually ship an executable that will load up the Haxe file. This is maybe more of an advanced thing if this is your own, your own system, and you're not really exporting it to other people. And it's actually a little bit like how Android works. If you kind of think of Android as an executable that loads up the Haxe library as a runtime, and then calls some stuff in that. So whichever way you want to do it, it's best if you can ship source with your library. You can combine it with any of these other steps I've mentioned, like ship a DLL for the common case, still use the source. And yeah, this is the approach that I've moved everything to in hxcpp now. Just ships the source for the PCRE and none of the binaries, and it just links. And because it's a small amount of C code, actually doesn't take very long, and it solves a lot of my problems trying to generate binaries and ship them. So now that's about what you might have that you want to help integrate, and we're looking at now integrating into the CPP source code. There's a few options. You can use the extern and the native to define an interface, and this gives you the strongly typed view of the C++ functions, and that's actually I guess the recommended way now. The inline CPP, which was the old way where you would generate a fragment of, like a little string that gets injected into the source code somewhere, and I'm saying not really use that now. It has a couple of issues. A, if I change the implementation, it might no longer work, and B, the compiler does quite a few things now with creating temporary variables, and if it's all inlined and untyped, it doesn't know what type of temporary variable to create, so it can end up creating an extra dynamic or something that you hadn't anticipated. Another way is CFFI or CFFI prime. This involves writing some native wrappers around your code, which are then resolved dynamically using a kind of get proc address style, and it's kind of the sort of safest option. If you can ship one of these, then you won't really run into problems with versioning or anything, and the code is so independent of hxcpp that it can run on Nico as well, so it doesn't even need to be running on CPP for it to work. Another option is to tightly bind your generated code to the Haxe generated code. Your Haxe generated code to your library code by including one of the header files from your non-Haxe code. So you actually include hxcpp.h and then start manipulating the variables directly. You may run into some issues with that. Certainly there's versioning that if you compile your stuff with a different compiler flag than Haxe has been compiled with, it could just simply not work. I'll go into a few more issues with that. And then hx native is an experimental thing. No one's really using it in anger, so I might just ignore that for now. So writing a native extern is kind of the preferred way of referring to external code directly. Have I got an example? Yeah. So here's an example. This extern class native. It's got this static function, public static function printx, and I've said native printx. So this has told the Haxe compiler that there's a function called printx actually which will take anything, because it's just, I've got type T. That's probably a bit more unusual. Normally you would restrict your things that it can take. And so when I refer to it in the code using native.printx, it will refer to it in the generated code using what's in the little native meta there, which is capital T printx. So that's the preferred way, and in this way the compiler knows all the types involved and can then make more optimal decisions based on what types to do. So just trying to think how to show this. I'll just go through it. So you can include native code into your generated CPP code using a metadata include on a particular class. And what this does is simply copies and pastes the code from the file that you refer to and puts it in the C++ code. The good thing about this is that the code comes after all the header files have been included, but before the C++ implementation runs. So the included code can see all the header files, and so it can access all the members that it needs to, and the C++ implementation can see all the native code. So they can effectively talk to each other in a fully typed way. And because it's actually pasted into the generated code, it gets compiled at the same time and therefore has all the same flags, and everything will just work out. There's sort of no versioning issues. With a native class, you can also specify a source file here for where it's actually implemented. If you use the // notation, it'll pull it from the same directory as the .hx file. And this can be quite useful if you've got a library that might end up on someone else's machine in a particular directory, and you don't really know where that might be. If you use the // you can ship the CPP code next to your hx code, and it will never get lost and never need to kind of resolve the path where to find it. So these previous inline CPP methods, I would say, don't use them unless you really have to. There might be a case where you want to squeeze in a this pointer or something using the CPP code, but try to avoid it if possible. So the code injection I spoke of, you can inline CPP code here. If you look at this example, I've got CPP file code, and what that is doing is pasting that piece of code smack into the generated code. And this works, but you can see here I've used my single quote here for the metadata because I want to use my double quotes inside my printf statement. I have to double backslash the /n because one is that's to make the backslash into a string because it's inside a hash string. So the quoting can get a little bit tricky. If you use the single quotes now, can run into issues if you've got a dollars in there and it's going to be string interpolated. So it is for a little snippet or for actually doing a bug report. I really appreciate it if you can put it in this form where it's just a single file and I can just go paste run and it will just compile. But in production, you're better off putting those lines in a separate file and just CPP including them directly. So there you can put code in different spots here. There's into the file, which as I said goes between the header and the generated code. You can put it in the header class. You can put it in the header, which would be to include something that the whole class wants to know about. You can put it inside in the header class code. Actually puts it inside the class definition. So you can put some little extra members into the class that hxcpp doesn't really need to know about. So you're just injecting raw strings in there. So that way you can kind of get the CPP output to look like it wants to. So this little code here works. It's using a template. I should probably use count rather than printf, but I'm old school. But it's you can see here this fully compiles, injects this printf code in, then calls it from the native. There's no untyped at all going on in here. The Haxe compiler's fully happy with all the types going on. Now, I guess in a larger scenario here, the CPP file code, that would be calling into your library to do something more interesting than just printing something, you know, create an object or something. So another way is with CFFI. This creates a library that does not actually that only ever refers to Haxe objects using an opaque type, which is just saying this is a value. I'm not really going to tell you what's going on inside it. You just know that it's a pointer to something, and then you can query the number of fields and convert it to an int and stuff from it. But because it's opaque, it lets the runtime decide how to implement these functions. And so you can write the same piece of code can run on Nico and on hxcpp, and possibly some other targets depending on how adventurous you are. Forms a nice isolated API that you've got to put in a little bit of effort and you get a clean API. So it's this kind of trade-off. You can't just go calling stuff with an easy kind of arrow notation. It's all a little bit verbose, but the end result is something that will survive. Like if the user upgrades Haxe, your DLL will still probably work because there's not a lot of difference as once you're in the CFFI stage. As I say, it's a little bit more work. Have a quick look here. This example is just from the hxcpp test. This is for, I guess this is the classic example here. Add ints. So there's your native function. Add ints takes 2 ints, returns a single int. And I use this define prime 2 for 2 arguments, and that wraps the whole thing in a dynamic function that gets queried from the C++ code. It says find me the function called add ints, and it can then pass it 2 integers, gets the result back as expected. So it's not that hard to write these externs. I'll just quickly point out this implement API. In the static link case, in this case, means that you're compiling this file here as a static library. Normally, C++ will use getProcAddress to get these symbols out, and the getProcAddress takes a DLL handle, and if you statically link, the DLL handle is actually the executable, and it can get a little bit funky. So the static link defines this implement API, which actually causes each of these defined prime routines to push into the CPP runtime a thing that says, if you want to find add ints, the function pointer is here. So this is a way of being able to run the same code either as a static library or as a dynamic library. There's also this Nico compatible, which makes the define prime macro also create the glue for running via Nico. So if you don't put that in and you try to run it via Nico, it will tell you that Nico can't find some symbol, but if you put that in, you can make your library kind of dual runtime. So most of that's all pretty straightforward. There's a V here for void, that's no return. You'll be using explicitly creating auto GC roots from the values if you want to hang on to them on the in your C++ code. And the rest of it, I think, is pretty straightforward. Oh, the hx string is an interesting one. It's actually got a string pointer and a length, or a stru and a size. I might change the string implementation. This will still work. Currently, this is the most efficient way of doing it, but it might become not the most efficient way of doing it. So I'll have to see how that goes. But either way, I can still make this work. So yeah, if you have a look at that, and then I guess I can quickly go to the calling of it. You can see here these functions. If I find add in, yeah. So these are using lib.load. Lib.load here is going to be either nicolib or cpplib, depending. Prime is the name of the DLL or the project, name of the function, and the number of arguments. Oh, this is, yeah, that's not the CFI prime, that's the CFI. So this is similar. You can see here the add ints, and it's taking this Java style type signature, III, which takes 2 ints and returns an int. And it uses a macro to generate a strongly typed function, so that when you go to call it, have I got an add ints in there? Yeah, add, because it's stored in a variable called add, 2, 5, and so actually once you've set it up, calling it just looks like a normal Haxe call. It's strongly typed as well, so if I put 2.5 in there, it would tell me that 2.5 should be an int. So the CFI prime is quite a nice way to set something up.
Why is it called prime?
Yeah, it was called prim. So all the Nico stuff is called hash define prim something for primitive, and prime is better than prim, so I stuck an E on the end. Yeah, historical reasons. Yeah, any questions on that actually while I'm here? No?
What was that header class code? I didn't really get the distinction between the header code and the header class code.
Yep, so header code goes in the header at the top, and it can be seen by the whole class. The header class code goes inside the class definition, which lives in the header. So it actually goes into the class declaration itself. So you can inject members into your class, or in fact anything. Right. Functions, members, yeah, just verbatim. Yep. So just here, warning against including hxcpp directly. First of all, it really needs to be the first non-trivial line in your file because of precompiled headers. So if you don't include it, your first line, and you try to link with a precompiled header, you get a compile error. I had a recent one where it was included twice, once at the beginning correctly, and then once from another file as well. And the error you get doesn't say you've included a precompiled header twice, it says something weird about unexpected something or other. So yeah, just watch out to include that exactly once at the top. But if you do go down that path, it is quite nice. You can just call your function members in a fairly natural way. You have to kind of know how the CPP code is generated, like all the objects are actually smart pointers to the object, and so you kind of use arrow notation. But if you look at the generated code, it shouldn't be too hard to work out how you might want to go about that. So yeah, native gen, I actually might just skip that. So that's kind of your options for like a broad level architecture of how you're going to link to your code. You're going to get it compiled on the developer's machine. It's all going to stick together. And part of how getting all this to work quite easily is this hxcpp build system. Now, the build system is a custom format, and you go, do we really need another build custom format? And I think it probably, yes, because I think it's definitely saved lots of grief without having to say, go down on Python and use Gradle for this build system. Oh no, actually we've changed it to Ant, or no, actually stuff Ant, we're using Bazel now. Like this kind of thing can be quite painful. So even though it is a bit of effort to write the tool, I think just the sheer number of targets we support, I think has paid for itself. And you got to bear in mind too, it's not really a general purpose dependency builder kind of thing. It's very much targeted at getting a list of files and a list of compiler flags and a list of linker flags together. So almost all the syntax and everything is all about just getting lists of files and flags. So there's nothing really too magical. It's very specific to compiling. So if you look, there's the build tool will run a compiler and it will run a linker. And there's not really a lot of scope for running something that generates something else separately, which is what we had with the TensorFlow build system. That's the library provided by Google. But their build system, first of all, you need to build some of the files into a library, then compile that library into an executable, run that executable to build another tool, use that tool to build some generated files that you include in another library. I bet they're wishing they had macros at this stage. And then that library is used to generate some type information that is used to generate the Python files. So this is their build procedure, which is all well and good once you kind of work it out. But they've got it all inside their build system, which is very nice for them. But the way I would attack it from this is you write a hack script to orchestrate the compiling of these phases, and each of these phases is a simple build file that lists which files need to be built with which flags. So it's not general purpose, so you might end up writing it in conjunction with another little tool just to orchestrate the many phases. Now, who here is interested in the details of that? I can cut this talk short and not go over the details of that, or I can go over the details.
Question.
Yep.
Can you link library configurator executable with it? For instance, WX use WX config executable.
Yes.
It gives you the list of flags.
Yeah.
Compiling and linking.
So lots of things do this, like autoconfig or something. A general approach here is to run the tool once, generate the config file, save the config file off. Then if you need to do that on different systems or for different configurations, put all those configs in a separate area and have one flag that includes which of these configs to include. So I've actually got an example at the end of this. We can see that in action. But yeah, no is the general answer to that one. I prefer run the configuration yourself once. A lot of these things too, a lot of configuration tools like on Linux, it's about what stuff you've got installed on your own machine. So, do you have, Pulse Audio installed? Yes, okay, hash include Pulse Audio. There you go, you're configured. But that's no good if you're building this library for someone else and you're going to ship a binary and the binary that you've shipped depends on how your machine was configured. So really trying to avoid that kind of not built by me kind of philosophy, and really that involves a little bit of effort on the developer's behalf to get the config right, but I think it's worth it because for everyone else it's worth it. For you, maybe it's a bit harder. Yeah, so as I was saying, the build tool, I can go over it, but if no one's too interested. Yes.
A question about that. Do you actually need the XML? I mean, could you target whatever processes the XML without the XML? So could I like write a macro or something which generates all the information for the build tool without having to go through XML? Because I don't like XML. So
No, you got to dump it out to XML. That's,
okay, so
I
I
mean,
dump it out to XML and just read back in, and then.
well, yeah. That said, the build tool is Hexcode, so you can grab the Hexcode, fill up the data structures yourself,
Yeah.
and run that if you wanted to.
Yeah,
But you know,
that's what I mean.
yeah. So it's not set up as a library though. It's just a little tool. I mean, and it's going to be reading XML for the individual compiler configurations.
Mhm.
So you know, iOS compiler. And you don't want to be duplicating any of that crap. Yeah, I mean, as I said, it's very not really that XML-y because it's just a list. It's just, you know, you've got an angle bracket in a file versus a squiggly bracket in a quote. You know, it's not a lot of difference.
Yeah, but
Yeah.
I want to write Hexcode, not XML, so that's where I'm coming from.
Yeah. Yeah. The answer is no.
Okay.
Yeah.
I have a question kind of slightly off on a tangent. If I wanted to use some NME or some Haxe C++ in another project
Yep.
that's not, like for instance,
Yeah.
say TextMate or like trying to put something in, having a play with something, it's quite difficult, isn't it, I would have thought?
So you got to decide how you want to compile the Hexcode. I mean, you compile it. You can kind of reverse it, compile Haxe into an exe, and then load the other library. Then let it do its thing, and then it can call back into you. That's sort of an inverse way of looking at it. But you can compile the CPP into a .so library, like a DLL, which is exactly what happens on Android. So if you think of Android as this external application you want to write code for, this is exactly how the Android works. It builds a .so file. You've got to have some way of exporting symbols from that. I'll talk a little bit about this later, but so you can either call get proc address on you and then just call your stuff, or you can maybe find a single symbol and call that, and then you export all your symbols back into the main application. But it's not. So your bigger application could have used this thing I was talking about earlier, where it just includes generated code.h and then just boots up CPP and starts calling stuff. I mean, that will work, but it gets a little bit fraught with, like, you got to make sure that if the hex code changes or the hex flags change, then you're going to have to recompile stuff. So it's not trivial, but it certainly can be done. Yeah, does that answer your question? I mean, we can maybe have a little bit more of the specifics.
Well, no, I was just thinking, I had a look at the TextMate code, which is Objective-C and C quite a while ago. Obviously, it's kind of completely over my head, but I was quite interested in whether you could put NME in, like a little NME animation in TextMate. It's probably very, very hard. And then there's not really much information on how to go around mixing Haxe C++ within other languages that use C++.
Yeah, I mean, on some level, you know, so the Haxe is not creating any kind of magical functions. They're just functions. So you're going to have to know how to stick any kind of piece of code in there first. Like, if you want to stick a piece of graphics code inside this TextMate, you got to know maybe how you would go about it even without Haxe, right? You're going to have to link in some stuff, get a window handle, get some kind of canvas, write some pixels. So you're going to at least need to know kind of how to do all that stuff before you try to get Haxe to do it.
Yeah.
So
I got it to do some stuff with TextMate using their bits and stuff, but it's quite hard to sort of see the sort of full how you connect up.
Yeah. So the main thing, I guess, if you can think of it, first of all, as static functions is kind of the easiest way to think of it. You got a function, you do something to this canvas, pass it the canvas, and then the problem is being able to write Haxe code that does something with a canvas. It gets a little bit tricky when you've got an object like you've got 4 canvases, you need it to do something with this canvas, now you need to do something with this canvas. It's not an easy problem. I'm not sure that Haxe is making it terribly much harder.
At the moment, it's not very easy to use. Is it easy? I don't know. To use Haxe C++ without the graphics, say, as like libraries within.
So you can compile it to a DLL or a library and then link that in. So it's not all that tricky. How you then use it and what your API is going to look like might start getting a bit tricky. Maybe you create an interface that you then hold on in here, so you can call all sorts of different functions on it. But you're still going to have to deal with this. There's a thing with holding memory references, which I can talk about a bit later as well. Is probably going to be your biggest hurdle in that sort of situation.
I mean, for instance, with Node.js, I managed to get it to call something on Nico, for instance. So stuff like that sort of thing where you're mixing languages, you might even be quite interesting to be able to do. It's not like easy.
Yeah, I think if you persevere, you could do it for sure. So, the exact method, I guess maybe no one's done it before. It'd be pioneering work. You could publish it, have everyone flock to you, ask you how to do it. But if you have some specific questions, I think it's just a matter of just doing each step one by one, getting a little bit further, getting it to print out hello once you've connected and stuff, and then just expanding it out from there. Any more queries? No. All right, so I'll just show you what's here without going over it. Build.xml file. This talks about how you run it. Let's again run through the hxcpp build tool. You provide on the command line like a makefile. You can provide key value data for configuring it. Normally you'd say like Android equals 1 and you're doing an Android compile or something. And then this target is, you can just leave that off. It's by default it builds the default target, which will be set up to build a particular XC or something. You can configure it, as I said, with key value pairs. The format is an XML based parser, and it kind of it's quite simple, just runs top to bottom. So if it comes across something like a print statement, it prints it or echoes it when it hits it. You can set variables. You can conditionally include compilers or nodes based on these if and unless clauses. So if you have a quick look at this example here, here's a little example build file that it can print out different things, and depending on how you configure it with the who equals world or without the who equals world, or you can use the double bar for or and the space for and, just to conditionally bring in stuff. So that gives them a little taste. Just the top level commands. You can set variables, set them in the environment. Echo and error for debugging. Path is quite useful for a compiler. You would add this bin directory to your executable path, so you can just call the compiler. And that's how you can do things like, we'll just use cl.exe for the Microsoft compiler because we've located the binary path and stuck it in the executable path. These copy files, you might just want to copy a file before you start. Maybe you include files in the wrong area. You need to put it in the right area. Hash pragma once. The NVC C flags are at the top level because they are used in conjunction with the other compilers. So I couldn't really put them in the compiler. But the big one here is the files, where you generate a file list in your XML, and tags. I'll just quickly go over the tags. Each of the CPP files that you're going to compile can have these flag tags with them, and your compiler flags can also have flag tags with them. So you might want to direct a particular compiler flag only at certain files. And the reason you might want to do this is because if you change this flag, anything that depends on this flag is going to need recompiling. So some of the GC code actually really only needs to change 2 or 3 files. You don't really have to recompile your whole Haxe app just when you change the flags for these 2 files. So you can target those flags only at a specific file. The other use for these is optimization. So you can lower or raise the optimization level on a file by file basis independent of the debug setting. And this can be useful for a couple of things. One, sometimes it can take quadratically long to compile a file based on file length when you've got optimizations on full, so it can actually like take a minute to compile a file. And often that file will be just a bunch of data or something, and you don't really need to be fully optimized. Or you've got some files that you want to, that are kind of your runtime files, and you want them to be compiled with release mode no matter what the user's doing with their Hexcode. So there's some good uses for the tags there. The target, you kind of need to know about the targets, and there's a standard target called Haxe that if you want to inject a link flag into, you inject it into the link target. I'll touch on that briefly. This magic lib name is what I used for a little while for compatibility, where if you tried to compile, tried to link in the regex library, it would actually replace it with the inline regex OBJs. So it was just to ease the transition. And then you can define a compiler, which is basically an executable plus all its flags, a stripper, which is used by GCC to remove symbols for releases, and you can divide a linker, and the linkers can be either a static link, dynamic link, or an exe link. Pre-linker I don't really use. And then the files is really just a list of files, but there's that cache flag I mentioned earlier, compiler flags, and then I mean that's really what it's going to look like there. So you can list the dependencies as well. So if any of those files changes, you need to recompile the original file. Targets, I think I touched on already. Targets just have names. Targets is basically the final link phase. So that'll be the list of object files they need to file in and the link flags they need to bring in. You can merge 2 targets together. So this is how you can merge in the NME. Normally it builds into a DLL, but if you want to build it all into the Haxe file, what you do is you just grab the NME target stuff and merge it into your Haxe target, and you will take all the linking flags, and now the linking flags will be on the Haxe exe instead of the NME DLL. And the rest is something you can look at. Compiler, who's quickly on that as well. It's mainly a list of flags, and flags can be targeted at specific architectures like MM. Which style of precompiled header you use. There's really only 2, GCC or MSVC. Get version is the command you use in order to know if the compiler has changed and therefore whether I need to recompile everything. Linker and stripper. Linker is usually you'll define 3 linkers for a particular target: a static link, a DLL, and an exe link. You might not need all 3 if you know that you're not going to be using those things, like maybe Android didn't have an exe link because it was unusual, but actually there is one in there now. You can compile stuff to Android as an exe rather than as a SO, and it just seems to make perfect sense. So that's the kind of build system. And I think if you understand it as, it's really just a way of getting a list of files and a list of flags together. That's its sort of one and only goal. Is you can get a better picture of it. And I'll quickly go over the XML injection. So having worked out this build file format, you can influence the build file that's created for Haxe. So normally when the compiler runs, outputs all the files, and it also outputs a build file which lists all the files and they're all their relative dependencies. If you've added extra code to one of these files, you might need to add a link flag to the final execution compile. And that's where you can use build XML injection here. It takes this snippet of code and just pastes it at the end of the generated build XML file. You can see here it's using this lib name. It's using the $haxlib NME. The $haxlib is a build tool variable, special variable name that it should find the path to NME that's current in the compiler. Bin.dir is another special variable that will be something like Windows or Linux 32. libextra is another special variable that'll be something like -x86, and libext will be the .a or .lib depending on which OS you're on. So that's one way of adding basically link flags to the compile. Another possibility here is actually you can override the main file group and put your own files in there instead. So you can just get rid of some files from Haxe and replace them with your own. To understand that a bit better, you should look at the Haxe target.xml file, which is shipped with CPP, which lists all the standard files that go into a Haxe build. The generated build.xml file will then include that, and together they make up the sort of standard CPP build. So any questions with any of that? Or anyone want to go? Yeah, all right, it's getting a bit dry, I guess. So we'll keep moving. Playing nice with mixed memory models. So this is really the kind of trickiest part of the whole thing, is that you've got this garbage collected code, and you've got code that will either need an explicit alloc or free, and you really want the two to kind of work together. So, and there's two cases. One is where you're putting external stuff into CPP, and the other is where you're putting CPP into external code. So, so here, let's say we've got some C++ code that has a resource called buffer, and we really need to call delete on this buffer in order to free the resources. So here's just an example of how we might go about that. Here's our hypothetical buffer class. It's just got a data member which we allocate, which we do some allocation in the constructor and destroy it in the destructor. So we're going to wrap that in some C++ code. So first of all, these are the externs to that class. You can see here I got include./buffer, which means that if you use this buffer native Haxe class, your header file will have this include buffer.h in it, which means that it can see all the definitions. Native buffer, my extern class here is called buffer native, but I'm saying we'll actually just call it, the real name is buffer. I'm going to use buffer native so I don't confuse myself in the Haxe code. Struct access means that you would normally use dot value instead of arrow value, which is generally the case. You can see here static function create, which returns a CPP star, which is a pointer to the native buffer. Native buffer is the buffer, so because I've used the native code. And the native there is new buffer. So if you go create bracket x, it's just going to go new buffer brackets x instead in the code. So that's the sort of a classic way of exposing a constructor to hxcpp. And similarly, the actual name of a destroy is tilde class name in C++. So, yep.
How do you avoid that the output qualifies the new buffer with buffer native, because it should put it in a package of something?
It doesn't anymore.
It doesn't?
It used to, but I don't put the colon at the front anymore. There was some stuff actually in there. So this is also that's for a class. This is for a function. It was a bit different as well.
Right, I was thinking about
Yeah. The C++, I think, handles the class native. Like the compiler doesn't know about native on a class member, only knows about it on a class, I think. Can't remember now.
I don't think so.
Yeah. with the new as well, I had to detect to see if there's a space in the native function name and put extra brackets in, because C++, in Haxe you can go new function dot do something straight away.
Yeah.
That actually binds the new incorrectly in C++ syntax, like the buffer dot does that, and then this new sitting out the front, he goes, what the hell is this new doing here? So I just put brackets around the new call in when I make it native. Yeah, and the destroy actually, tilde buffer, that's just another little thing. So you'll end up calling native just dot destroy, and then I'll call native arrow tilde buffer, which is actually what you want in this case. So having created the externs, what I'm going to do is make a wrapper class for it. So here the buffer wrapper is going to extend finalizable. Now, if you wanted to have a finalizer, you don't actually need to extend finalizable. If you go and look at that code in the stdlib, all it does is in its constructor it adds a CPP call to finalize. So I'm just extending it for, I guess, sort of for convenience. Then I'm going to override the function finalize down the bottom. So here I create the new buffer, and I've added a function here, release. I think if you're going to do kind of native interactions, I wouldn't be necessarily waiting for the garbage collector to run to free your resource. Quite often someone is actually going to want to explicitly free that resource, because it could be minutes before the GC is run. So you give them the option by calling release. I mean, this is like dispose of bitmaps in Flash. It's all kind of the same concept. Here I've wrapped the print. I mean, I could just expose the buffer here, so you could just go buffer wrapper, buffer print, but I think putting it on the class, I mean, you could make it inline as well, just to make it a bit more efficient. But maybe there's also some things you might want to do in converting from Haxe types to native types, so that this wrapper class actually is all just very, very Haxe-like from the outside, even, and it hides all the kind of implementation details. And here finalize, it calls the buffer destroy, which deletes the buffer. This will get run by the GC a bit later. So having a single wrapper class for the pointer, you know, maybe seems like a bit of overkill, but it really solves the problem of deleting this thing exactly once. I mean, you know, in the bad old days of C code programming, you would allocate something and maybe pass the pointer around to several guys, but it takes a bit of effort to work out who actually owns it and who's going to delete it, even though you've got a pointer to it. Here, it's this one buffer class that owns the buffer exactly once, and there are many Haxe classes can point to this buffer wrapper, and once they've all finished with it, then it will be deleted. So it's sort of like the shared pointer concept with C++, and kind of I don't know, I guess it's the recommended way of wrapping your class.
But who causes the finalize call? I didn't really get that.
Yeah, GC does. So once there are no more references to this buffer wrapper, in the next GC pass, you'll get a finalizer callback.
So it calls all fields called finalize, or
Yeah,
is that connected?
There is connected because it extends CPP finalizable.
Okay, so you have to extend it.
You don't. If you look at this class, what it does is just goes. It sets a static function callback on this class, which happens to be called the finalize function. So it's easiest if you do. If you don't really want to, you could work around it, but let's just say, yeah, that's the way to do it. Yep. And I'll talk about the finalizer in a little bit. You've got to be a little bit careful with your finalizers, but you know, deleting something is the classic use for it. So this is talking about creating the wrapper, and so that's for when you create an extern and put it inside your member function or member variable or an array variable or map variable. But if you're just going to put it on the stack, which means a local variable or a function argument, it's all right. You don't really need to worry about it so much because the C++ code will destroy itself. But you do have to be careful if you're going to store stuff in members, like std string. I guess idiomatically in C++, you just have those as a member functions, no worries. Use them and they'll take care of themselves. But you can't really have a member function that's an std string in your C++ code because the destructor will never get called. So because the garbage collection doesn't normally run a destructor. You could add a finalizer and get it to call destructor, and you might be able to get that to work, unless GC moving's there, which actually just byte copies code from one place to another, and therefore that might screw with your pointers. It also gets initialized to 0, so you might think the std string is running a constructor, but actually it's just getting mem set to 0, which may or may not be the right thing. Often it is the right thing, but you don't really want to rely on it. So if you're going to store something like an std string in a class, I recommend storing a pointer to an std string, even though it seems like a bit of extra load. It's just going to be easier to deal with as far as these sort of just resource management. The CFI abstract, the abstract here being overloaded term, but that's where from your CFI code you create a Haxe object, you add a finalizer to it. So normally you'd create some data and attach it to a Haxe object, and when that Haxe object is no longer needed, you get your callback and you can delete the data. So that's the way we handle that. In NME, I actually only have a single class object from which all resources derive, and that object has a virtual destructor, so I really need to care about this once. So if I create a thing which inherits from object, it automatically has a destructor tied to the Haxe finalize. And this is what I was talking about earlier. Be careful with your finalizers, because I guess the finalizers might not always delete something. You might want to do a dec ref, that's fine. With the WX implementation I had, which is not the same, I had a sort of a different kind of aspect on it, where I'd create just a normal WX object and I would attach the Haxe class in the client data for that object. Now, if this Haxe object goes, I don't really want to delete the whole WX object. I would just want to delete the client data. And similarly, if this object, the WX object disappears, what I do there is I null out the back reference to the class data in the Haxe class. So you have to come up with some creative ways sometimes for keeping the object references in sync. So similar, there's some stuff goes on with Java as well. Haxe can hold a JNI object reference and it'll create a JNI GC root when it does. And similarly, Java can hold a Haxe reference. It stores it in its long, but we can typecast it to a Haxe object and has to have a GC root associated with it. So it sort of gets a little bit tricky here, but I guess you could maybe ask for help specifically on something. And so just warning about finalizers is that they could be run from a different thread. So they could be run like the collection is run by the thread that makes an allocation call, and that is the thread that usually calls the finalizer. Although I reserve the right to call all the finalizers in threads at some stage. So there are some things that you can't do from a foreign thread, like OpenGL deleting resources. That's probably the biggest one. And also calling Java. Sometimes you need to native attach to Java, JNI attach, before you can do something in that destructor. So you just got to be a little bit careful about what thread's calling the finalizers. You need to check threads and push jobs. Yeah, so that's the strategy that NME uses for OpenGL, is that destroys the text resource. I'm not on the OpenGL thread. I push it onto a list, and on the next render on the OpenGL thread, I find that there's this texture that needs destroying, and I destroy it there. So it's a little bit hard, I guess, but it is sort of a bit of a fact of life. So this was talking about GC roots. I guess another way of avoiding some of these GC root options is to actually just have a static array of objects in your hxcpp in Hexcode. And then if you want to store an object, you can just stick it in your array at element 37 and then pass off the number 37, and that becomes like a handle to your object. And then when you go to use it, you can just look up object 37 and return your pointer. And that way you can kind of skip some of this GC root stuff altogether, because it's just running in Haxe with just object IDs. You still need to manage it. Like once you no longer want to hang on to object 37, you need to null it out add 37 to your free list or something. But there's sort of some ways there you can work around needing GC roots. GC roots are quite easy in CFFI. There's just functions for it. And if you're doing the hxcpp route, there's those two functions there, add root. You probably need to typecast, static cast your pointer to an object star star, because it's probably not going to be an object. Or you can use that array technique I mentioned. All right, so that's kind of memory referencing and stuff. You have any questions or comments on that? Yep.
You say the finalizer when the GC runs?
Yes, it runs after the GC. That's right.
What triggers the GC?
Usually a memory allocation call. So anyone does a new function at any stage, it's potentially a time where the GC will run.
So for instance, if you don't do new, it's possible that GC never runs
Yes.
until you...
Yes, definitely. And if you object pulled everything as well, it'll never run. And that's why I recommend a dispose function, and really disposing of stuff as soon as possible.
And when you quit the application, does it run the final
Uh,
class, or-
No, it doesn't. There is an exit handler, I think, and you can explicitly run GC. Maybe to run all the finalizers on a GC. I mean, it depends if you do it on the destruction of a static object. Things like some DLLs can get unloaded before your finalizer runs, and that can get awkward. You could possibly put it actually at the end of your main function, just have a GC run function, depending on whether it's a GUI app or not. Yeah. I mean, I could maybe expose the finalizers, and you could just run through them yourself and call them if you wanted, or something like that. Yeah, if you need some help there, we can come up with something, I think. Yep.
I had a question about the part where you include the buffer file.
Yes, yes.
So if I understand this correctly,
So there's the buffer wrapper, or no, just the buffer the native. This one?
so the root buffer.h that will just generate a C++ include line, right?
It actually, yes, or one of them pasted the code in, and one of them includes an include, but it'll be a full path to it, so there's no worries about include, like which path is included. But yes,
Well, because it's relative to the hex file.
yeah, it gets converted from relative to absolute if it starts with // It's like a special code. Other thing, yeah, so it knows where this particular hx file is, so it'll takes the directory path of it and replaces the // with the directory path and includes that whole file there.
So the header file gets copied over to the destination.
No, it just uses a full path to the buffer line. Well, actually, let's have a look. So, is it in here? Which one was I in? Must have changed the files. You can see here actually the square brackets after the files. That's the list of tags that are used for that file. If you want to, you can see here, for instance, that the static flag only affects lib and stdlib. So if you change it from being a static link to a non-static link, those are the only two files you need to recompile. So cpp source. So you can see here. No, you can't. Yes, include C issue dev Haxe Summit 27 code buffer buffer.h. So it's sort of straight in there. So this code can now effectively see that, so that when I do a new buffer call here, it knows what buffer is, can call it.
So where's that file now? Compiled situation?
So because this, so the generated file is under this CPP directory that I gave on my command line, and this here is from where it found that hx file, which will be in your Haxe class path. So in this case, it's just in the current directory was where it found it. But if it had come from a Haxe lib or something like that, and it was under C, Hex toolkit lib something something something, it would actually be including C Hex toolkit something 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 on that line there. So, yep.
Is that macro check for the existence of the files?
It's a good question. Should we have a look?
I'm asking because of the integration maybe with the compiler cache.
Yes, actually I did do something there where it actually pastes the code in for the CPP file include, which means that if the code changes, the CPP code will change. I think maybe in this case I should inject a dependency on that buffer.h. Otherwise, if I change that buffer.h, it won't recompile. So you're right, there is something there. So if I rename the file, it just what I said. It didn't bother recompiling it because it didn't see the change, even though it did change. Yeah. So, well, in fact, I should add it to the dependencies myself because I know I've included it. So I think actually that would be pretty sensible. If it had sub dependencies where it included something else, might need to add them some other way. I'm not sure. Any other comments?
So with that buffer wrapper thing,
Yep.
can you pass like say a time or something to it?
Yep. So you just need to make sure your types match. So if my buffer took a float time, I could pass a float to it. If you're talking about the buffer taking a Haxe date class, it becomes trickier because now the buffer needs to know about what a Haxe date class looks like.
So you could just convert it to a float and then pass the float.
Yep, for sure. So
So that would you just put it in the parameter.
So if I wanted to do, if my buffer.8 actually in here took a double D and so that would be the buffer, and then the wrap, the native, I would have to add it here. So this is the create function here, which is actually my constructor. I'm saying it takes a float. Float is equivalent to double. Now, there are actually two things. There's a float 32 and a float 64. If you want to be explicit about the size, it's normally assumed a double, which is float 64 for everything. In fact, but in this case, it doesn't really matter because you can type the extern as a float, which implies 64-bit, but you could take a 32 or a 64-bit. Usually it wouldn't matter. So that's that, and then the test would is it going to work? No. Print. Did I say print? 16. Oh, new buffer wrapper. Yep. So I wrapped it. So I pass it on actually. which is so as long as the types are, I guess all the CPP standard basic types are quite easy to work out because there's no real object ownership to worry about, and you just pass stuff off. String actually also passes off pretty well. Like if you take a const char star, you can pass a hex string to it, pretty much just sorts that out for you. So yep, that's a question. Pixels, so you could do a pointer to an integer is probably the way to do an array of pixels. Usually they are 32-bit, and then you could use bitwise manipulations to set Gs and Bs. It's probably the way I would go about that. And you don't really, then it's not really objects, it's still just integers. Can work all right.
What would happen if in place of this static create functions, you would try to use a constructor, like a hex constructor?
Yeah, so it's going to generate a underbar alec call or something like that, right? So it's because I can't use C++ constructor because of the out of line supercall.
Yeah.
So I have to have a pseudo constructor where I first of all allocate the memory, and then I call construct on it. So yeah, it's not going to work.
What if we go back to the buffer.hx?
Buffer.x. Yeah.
What if the buffer in declaration in buffer.h should have been inside namespace? Would you have specified namespace in native as well?
Yes, so this would just be, that would then become namespace colon buffer for native. So I can put the buffer native in its Haxe namespace wherever I want, and then specify the native with a namespace wherever it wants to be. So it's, you can kind of move the namespaces around arbitrarily without a problem.
But then how does new buffer work if it's in a new namespace? Because that would
Yep,
be
so it would need to change as well.
Yeah.
So that'd be new namespace colon buffer.
okay.
Yep. Yeah. Yep.
Might it be possible to automate this?
Yes, it would. You know, there's this swig stuff that they do. I often dream about maybe trying to do a bit of that. But I think, some classes you do need to kind of come up with a ownership policy, maybe per object. Like there are some things which you can do with a struct, which actually doesn't really have any ownership problems because it's just copy by value and use values. So that works out all right. So it's sort of making some decisions about whether you want to store stuff as a pointer or as a struct. You kind of make that once. I think you definitely could automate it, and perhaps even should. Parsing a C++ header file is a job for Swig or something. But, you could do something like the AS3 guys where you annotate something to give it some type hints and then just run some basically text processing. That sounds like a pretty sensible way for going with a big library. At least you get it robust and repeatable.
It looks a lot of error prone.
Yeah. It is type checked at compile time, so of the C++. So you can get your Haxe will compile fine, and then your C++ will go, no, this can't compile. So you kind of get a secondary check on it there. But yeah, you're right. No one wants to write too much crap by hand.
To respond on that, Clang has an API you can use. So it parses your header file and exposes it in a nice way. And that's the issue. I tried, but it's C++ does a lot of things Haxe can't do. So
Yeah.
you run into issues if it was the other way. Easy, but
Yeah, in some.
to express some things in C++ in Haxe which don't have equivalent.
Yep. Yeah. I mean, that's actually what this native thing I referred to earlier was about. It's really about defining an interface. So if you can define your API as a series of interfaces that only ever refer to other interfaces, actually things become simpler. But once you start saying, well, it's a template with something that C++ can do, even enums we've seen can cause issues. So it does get a bit hairy. No other.
One,
yeah.
sorry,
Yeah.
can you use this with MM classes? So you can wrap any C++ code like the MM Objective-C stuff?
Yes, yes. In fact, so if I were to tag this class here with the objc metadata and compile, when it goes to actually call this print, it would call square bracket object print square bracket like they do in Object-C. So just same function, just sort of a different calling syntax. All right. Abstract, talk about file, talk about. Okay. Threads and stacks. So I put this documentation in CPP. Really talking about some considerations you have to worry about with threads and stacks. Does anyone want me to go over this? I can go quickly or slowly or not at all. Can you not at all, really? I'll go over it super fast, maybe. So normally your threads, if you call thread create from Haxe, it's a Haxe thread, and it can do all the garbage collection, all the allocations and stuff. Not a problem. When I've designed the GC, I'm actually relying on the fact that I've got control over all the threads that want to do GC, and it comes to this phase called stop the world, where actually ask all the threads to stop doing stuff so that I can do the collection. And if someone goes changing something while I'm doing the collection, it just messes up the order of what I think's marked and not marked. So in order for this to happen, I've got to make sure that all the threads have stopped before progressing. Now, I don't actually technically have to stop, but they have to stop making GC calls. So I've got a thing where you can enter a GC free zone where you're saying that you're not going to make any garbage collection calls. Then you can, or allocation calls really, then you can go off and do whatever you want. And this would be like waiting for a mutex. So before you go and acquire a mutex, you enter the GC free zone, you acquire the mutex, and if it takes you 5 minutes to get that mutex, that's all right, because the garbage collector is not waiting for you to come and participate in the garbage collection before moving on. So it's an unfortunate implementation details in some ways. Almost all GC systems have some stop the world phase, and I think this enter blocking, exit blocking is quite a nice compromise, besides sending some kind of signal that halts your thread, which can be non-platform, doesn't work on all platforms and gets a bit hairy. So some techniques that you would use here, like if you're going to have a socket that reads data from a potentially slow connection, you would allocate a buffer, then enter the GC free zone, where you would read the data out of the socket using the native call, but you're not making any garbage collection calls, and you're filling up the buffer, and then once you're done, you'd re-enter the GC zone, and you can do more calls. And a little trick to watch out for there is, if you throw an error or something, you got to not be in a GC free zone when you throw an error, because it needs you to allocate a string, and it gets a little bit hairy. I mean, if you use the CPP primitives that I provide, should all be set up for this, so you don't really need to worry about it. It's only if you're writing your own code with your own, we got a Haxe thread running through your code, and you're going to make a blocking call, you should enter a GC free zone. And then conversely, native threads are not registered with the GC system, and therefore not help out and not participating. And you've got to make sure that they don't go around changing pointers in the middle of a GC operation. So this means that if you want to make a call from a foreign thread, and a foreign thread might be if you've just gone create thread in your C++ library, you've got to make sure you're attached to the GC system, and that's done with set topper stack. And then when you're done, you can detach, go off and do your own thing. A few things to think about with foreign threads, again, like the finalizers, sometimes you might not think you're getting a foreign thread, but you are, like audio callbacks is a classic one where you get a callback from SDL to go fill up some buffer with data, and you go, okay, let me just call into Haxe. You're actually in a foreign thread when you do that, so you can't make any garbage collection calls. Just sort of something to watch out for there. So there are some other techniques to get around that, is if you don't want to attach and detach, you can put the work from the foreign thread into a queue, and then have a real Haxe thread visit the queue, fill it up, and then retreat, and then the foreign thread can pick the data up and put it back. So there are kind of ways around it, not necessarily easy, but it can be done. And with the Android target, because the thread is actually the render thread, which is different from the UI thread, you really have to start thinking about threads. And for that, in each callback I get, like render frame or mouse clicked, I attach the thread to the garbage collector, do the work in Haxe, then detach and then carry on back into the system. So something to think about there. Just a quick look at terminology. Top of stack. Historically, stacks start at the top of memory and then go down, and usually Alex start at the bottom, go up. But it's not really the case, but they almost all do start numerically higher and go down as you push variables on the stack, except for mscriptum, which goes up because it's different. But and you'll see that the variables, local variables and function arguments get pushed on the stack as you go through. So if this is an imaginary stack at address 10,000, it starts the program. There's a few local variables on the stack. Then it hits this call here, set top of stack. It just creates a little temporary variable T0 and then passes the address of that off to the GC system. And what that does is records the position of T0, which might be something like you hear in this example 9976, as the top of stack. So what it's going to do is any variables below that on the stack are going to be considered potentially Haxe variables and therefore need to be traced for garbage collection. So at some stage in the future, many calls deep, something calls allocate enemy, and then that causes a collect call because it's run out of memory, and inside the collector he'll start a new variable bottom of stack, which might be at let's say 8050, and therefore it will now do a scan the stack from that 8050 to the prearranged 9976. So that's the range of variables that it needs to scan, and any variables it finds there won't leak from the garbage collector. You have to be a little bit careful using this technique when the main returns immediately or something like this. This kind of thing happens in something like iOS, where in your main line you start the CPP running and then you register a callback and then you actually just exit the CPP code. But in some stage in the future you're going to get this callback on your CPP code. Or maybe it was very deep deep down the stack that it made this call. So actually your top of stack ends up being quite deep down, and then when this callback happens it comes up higher up the stack, and now the top of stack is actually below the bottom of stack. This sort of thing can happen, so it's, if you find yourself having to think about it, you maybe come back and have a look at this documentation, but there are ways around it, like this this parameter here, the final parameter set top of stack, is whether to ratchet up the top of the stack. So if it finds a stack higher, then it goes, oh, actually that's the top of the stack. So it always keeps the sort of the highest number in the stack, or whether it attaches and detaches is your other option. Those are probably sort of two options. Debugging, there's a printf in the collector that can show you which range of variables it's marking. So if you've got a static variable, a local variable that's missing GC marking for whatever reason, have a look to make sure that its address actually is in the range of the conservative range, and if it's not, then maybe you've made a mistake or there is some problem with the stack attaching and detaching. All right. So that, any questions on that? No? Yeah, I guess that's more of a, like, if you're writing a GUI application in a new sort of framework, you will need to think about that sort of thing, but until you do, probably not going to mean that much to you. So there's a few things I've got here. If anyone wants to go over them. Got wrapping a library, got an example about how we can use JPEG library and then make some externs for it and then run it, or and then how to use it with hxcpp. I've got an example of an external tool chain for cross-compiling Raspberry Pi, or I can go over something else. So, or we can call it a day. Can go either way. So this documentation here is in this Haxe Summit. So the wrapping a library is a worked example. 1, 2, 3, 4, 5. The actual answers are in this directory, so you can go over that in your own time if you like. And again, the CPP direct. It's quite similar to what we just saw. Here I inject a bunch of extra flags into the Haxe target, and I put the pixels somewhere. Yeah, this is the JPEG callback, and I had to hack the JPEG example just a little bit, actually, what was I? But hardly at all. So it didn't need to change very much. Quickly go over. So all I did was here, I made this a const char star instead of a char star. Just easy to pass a hxcpp string to it. And here, because this file is injected into the generated file, it can see all the definitions. And in the example, it kind of left this put scan line somewhere to be provided by the guy using the example, which is me. And here I've provided it by calling this static function JPEG example obj put scan line somewhere. Which this obj, this underbar obj is the way the static class is called, and the member class is without the underbar obj. So they're the only two little changes I made to that example in order to get that to work. But you know, I guess it's been a pretty long presentation, so I can leave it there, unless anyone wants me to go over something.
Just about libraries, how do you deal with versioning if some part of the API only exists after some specific native version of the library? Can we define that somehow? Do we use conditional compilation?
Yeah. So when you ship, if you're providing the source code, you're providing the Haxe code at the same time, then they will be in sync for sure. Like if you want to say, let's say this is JPEG 9. Say there's some feature added in JPEG 9 that wasn't in JPEG 6. You want Hexcode. I mean, he can see the header files, so he can go in you can put the Haxe function in, can check the header file using some native code, like if hash define is greater than 16, then you could throw a runtime exception.
Yeah, but we don't want that. We want to catch it early. So
Yeah, well, I'm struggling to think how it would work, because in these examples I'm shipping the Haxe and the source together, right? So they will never be out of sync. Now, if I have, so I've put the source and the Haxe code together in a Haxelib version 1, and then I do version 2, which has this extra function in it, and you've got old code using version 1. You're at the same stage you are with any Haxelib, where you can use your Haxelib defines to go if Haxe version 2, I can call delete, whereas in version 1 I couldn't, or something like that. So it's really just using standard Haxe, conditionals there, or yep. So yeah.
Can I do that on Mac?
Sure can. No. You can. It's left as an exercise for the reader. So it actually won't be very different at all. So if you have a look here, I've set this SDK. You could almost do it exactly like that. So you'd find an SDK for cross-compiling. So you'd have to find somewhere to download that. So it'd have to be a Mac cross-compiler to Raspberry Pi, and it'll have a GCC call in there somewhere. So really just a matter of finding where that GCC call is and putting that in the in the XML file, and then you can see you just need to write these sections here, the linker and the path, and see, it is really quite small. So this is I find this quite a nice way of doing things, setting a default directory unless a variable exists, in which case we just use that variable. This way someone can set the SDK using their hxcpp config, and it costs you nothing to put the default in. Path, so this is adding to the executable path. In your Mac scenario, that'll be something quite similar, if not exactly the same actually. And then the exe prefix, this is there's quite a mouthful here: Linux, ARM, GNU ABI, hard float, and then includes the standard GCC toolchain. But you can see here that's defining the compiler. It's just saying the name is GCC G++exe. Add these flags, put the dhxrpy on there just so we can use it within the source code, and makes a .o, use -o. So it's really, I mean, you could copy this almost verbatim, I would say. And then for static link, the tool is called hxar, and you need a -cr flag instead of sometimes they have different flags for creating archives. The exe, I'm just going to add the dynamic load library, the C library, pthreads, and math libs, and the same with exe. So it's not a hell of a lot to it, and you know, because fundamentally compiling is just calling a compiler with a bunch of flags and a bunch of files. So it's really not that hard. That sometimes to find those flags, you can like maybe run the makefile and actually see which flags it generates and just cut and paste them into CPP. That's how I did the Android flags to start with. I just ran the Google thing and said, all right, paste those flags in. Now we don't need the Google tool.
I see a bit of code repetition there. Would it be possible to factor that out?
Yeah, there is some code repetition there. You can refer to files, actually. I don't know if I should put lib into files. So I can have a files entry here, which brings in a whole set of files into a target or a linker. So I should be able to have it can bring a whole set of libs in as well. Yeah, yeah, you could do that. The other one, actually, there are some, it just evolved that way. But yeah, there was some repetition there, I grant you that.
I wonder if you had tips on how to do CPR host with native externs.
Yeah, so if you can write that wrapper class, that'll work, right? Obviously a bit of a pain, but if you notice that buffer wrapper class I had no external references to C++ code. So I'm calling print on it, and internally it's calling buffer arrow print, but externally I can't see that. And in fact, that's some of those things where I'd actually might inline that print function where it chains it through. I would hash if not sepia inline it, so on the C++, or if not scriptable. So it will generate the glue function and sit there, and you can still call it with sepia kind of not directly as well. So that's.
Otherwise, you want to shoot convert hxcpp dynamic to the native class.
So yeah, so you can pass them round. Like if you have a CPP star and it goes to a dynamic, it's fine. It'll get passed around, and when you get it back, you can get the CPP star back out of it again. But you can't do anything with it, like delete it. Like you can't call delete from within sepia. So yeah, currently I've only really used the CFFI stuff with sepia. Mainly, although all the hxcpp runtime actually is wrapped in Haxe objects and called by sepia that way. So yeah, that would be my method at this stage, but maybe we can work on something if you got some ideas. Yeah. All right, we are done. I'm done. Thanks for your attention.